In practice, modern data science often requires us to precisely predict the exact count of discrete events within chaotic, real-world environments. Although a coin flip and a server request seem unrelated, we categorize these scenarios under one mathematical umbrella: discrete count data. To analyze these counts, we use three specific models: the Bernoulli, the binomial, and the Poisson distributions. Standard curricula frequently present these as isolated formulas to be memorized for specific test cases. In practice, these models scale into one another, forming a progression that moves from a single event to a chain of trials, and finally to a limit of infinite possibilities. Understanding this relationship allows analysts to derive the exact models needed for reliability and risk engineering, instead of relying on trial and error. The process begins with a single Bernoulli trial, one independent attempt with exactly two possible outcomes: success or failure. We define the probability of success as p. Since there are only two options, the probability of failure must be 1 minus p. Because the outcome is either 0 or 1, the average, or expected value, of this single trial is simply p. We calculate the variance of this trial as p times 1 minus p. This shows that statistical uncertainty is at its peak when p is exactly 0.5. This model is the building block for the more complex engines used to analyze large-scale industrial data. To move beyond a single event, we have to model what happens when we repeat that Bernoulli trial multiple times. The binomial distribution represents the sum of n independent, identical Bernoulli trials. As the system scales, the expected value becomes n times p, and the variance becomes n times p times 1 minus p. For example, if a production line has a 4% defect rate, a random sample of 20 items provides us with a fixed n of 20 and a p of 0.04. Calculating the probability of finding exactly two defects requires us to identify every possible order in which those two defects could appear across the 20 items. We use combinations, written as CNK, to count these arrangements. In a sample of 20, there are 190 distinct pathways for exactly two defects to occur. The binomial PMF takes this count of arrangements and multiplies it by the probability of the successes and the probability of the remaining failures. The binomial model is the correct choice for any environment where you have a predetermined known number of independent attempts. Some systems are too large for simple counting. If an airline sells 200 tickets and expects a 3% no-show rate, we are still looking for a count of successes. However, calculating the combinations for 200 trials results in a massive amount of factorial math that can become a computational burden. We need a way to model probability when the number of opportunities is high, but the chance of an individual event is very small. As n increases toward infinity and p shrinks toward 0, we replace them with a single rate, lambda. The possible outcomes grow, making the bars thinner. Though it resembles a curve, it remains a discrete distribution of distinct whole number counts over an infinite range. At this limit, because p is so small, the term 1 minus p is functionally equal to 1. Because that term is 1, the original binomial variance formula of np times 1 minus p simplifies to just np. This mathematical convergence is why the signature of the Poisson distribution is that its mean and variance are always equal. Effective data science depends on matching the model to the physical constraints of the system you are studying. Ask one question: is the number of trials fixed? For a set number of attempts, use the binomial model, standard for component reliability. For continuous events with no upper limit, use the Poisson model, ideal for tracking insurance claims. You must ensure the rate, lambda, corresponds exactly to the time or space interval being analyzed, or the model will yield results that do not align with reality. By viewing probability as a progression from a single Bernoulli trial to the Poisson limit, analysts move from memorizing formulas to building models that reflect the actual constraints of their data.